subscribe now and press the bell icon. Never miss an update.
Hi friends, myself Dr. Darshan Jani, and today we learn about important topic of chemistry, that is CC bond forming reaction. Also, don't miss to like and share the video, subscribe the channel Chemistry Online by Dr. Darshan Jani and hit the bell icon to get regular notification for such important videos. So let me start our important topic, that is CC bond forming reaction. As we can see on the board that CC bond formation is basically carried out by two ways. First one is addition reaction and next one is olefination. So let me start with addition reaction. Addition reaction is basically carried out by two ways, either by conjugate addition or direct addition. So it is important for us to define both this term, that is conjugate addition and direct addition. Also we should know about difference between conjugate addition and direct addition. So let me discuss this important topic. So we start with conjugate addition. So addition that occurs with nucleophile that are weaker base, right? Then such addition reaction is known as conjugate addition. And also we should know about the examples of that weaker bases. So thiol, cyanide, organocopper and enolates. So these are the examples of a weaker base which are act as a nucleophile to give conjugate addition. So next one is direct addition. So this will becomes exactly opposite to the earlier one, that addition reaction that occurs with nucleophile that are stronger base. Then such addition reaction is known as direct addition. And which are the example of such stronger base which can act as a nucleophile to give direct addition? So organolithium, lithium aluminum hydride, Grignard reagent. So all these are the example of such stronger base which will act as a nucleophile to give direct addition. Now the next part for CC bond formation reaction, that is olefination. As we all know very well that olefination, that is synthesis of olefin, or we can also say that alkene. So before we start, reaction which are used for olefination, we should know about certain basic terms, that is geometric isomers, EZ nomenclature, as we can see on the board. So these are very basic terms, as we know, or we should know about definition of geometric isomer. So it can be defined in a single line, that compound having or isomers having same structural formula, different arrangement of group attached to either a single atom, double bond or in cyclic system, then such two isomers or forms are known as geometric isomers. And we all know, guys, cis and trans are the example. So also we should know about what is cis and what is trans. So as you all know that if same group are on same side of double bond, then such form is known as cis, while if same group are on opposite side of double bond, then such form is known as trans. So there is one question in our mind, that if there is a cis trans nomenclature, then why there is a requirement of EZ nomenclature? So very simple things, that in case of cis and trans, there is a requirement of same group either on same side or on opposite side of double bond. But if all 3 or 4 groups are different, then we cannot apply cis trans nomenclature. In such case, we have to carry out nomenclature with the help of EZ nomenclature. So how this EZ nomenclature is carried out? So as we can see on the board, that if higher priority group are on opposite side of double bond, then this form is known as antigen, which is denoted by capital E. And if higher priority group are on same side of double bond, then this form is known as Zusammen, and it is denoted by Z. So by this way we can easily define the basic terms, that is cis trans and EZ, before we start important reaction for olefination reaction. So friends, next important olefination reaction is Wittig reaction. So we start olefination with two or more important reaction, out of which first one is Wittig reaction. So how is carried out? Let's see. So in Wittig reaction, when any carbonyl compound, that is aldehyde or ketone, react with Wittig reagent to give alkene as a product, then such conversion is known as Wittig reaction. How it's carried out? Let's see with reaction mechanism and example. So as we can see on the board, how we can memorize the conversion of Wittig reaction. So it can be carried out that carbonyl compound, that is aldehyde or ketone, react with Wittig reagent to give alkene as a product, then such reaction is known as Wittig reaction. So which type of reaction is carried out in Wittig? So as we can see here, that any carbonyl, whether aldehyde or ketone, react with Lide, phosphorane or Wittig reagent to give alkene as a product in presence of strong base, then such conversion is known as Wittig. So as we have discussed earlier, any reaction can be easily explained with the help of mechanism. So it can be defined as triphenylphosphine. As we can see here, triphenylphosphine react with alkyl halide to give phosphonium salt. Now what will happen? This phosphonium salt undergo reaction in presence of base to abstract proton from this particular carbon to give Lide or phosphorane intermediate, which is also known as Wittig reagent. Right now this Lide is react with carbonyl compound. How? We can see here that this negatively charged carbon will attack over carbonyl carbon. We know that carbonyl carbon is partially positive. So this pi bonding electron will be shifted over oxygen, and oxygen will give or get negative charge, and we will get B10 intermediate. As we can see the structure of B10 intermediate. Now this B10 intermediate will undergo bond formation between this positively charged phosphorus and negatively charged oxygen to give oxaphosphetane as a product, or we can also say that intermediate oxaphosphetone. And as we can see here that oxaphosphetane will undergo rearrangement or decomposition like this to give alkene and triphenylphosphine oxide as a product, and this whole reaction is known as Wittig reaction. Now as we have discussed earlier, any reaction can be easily explained with the help of example. So in example we can see that when any triphenylphosphine react with any substituted alkyl halide to give Lide, or we can also say that phosphorane or Wittig reagent, and this Wittig reagent will react with carbonyl compound, that is any aldehyde or ketone, to give alkene as a product. So this reaction is known as Wittig reaction. Also the modification or advancement of Wittig reaction is known as Horner-Wadsworth-Emmons reaction. Again this one is an important reaction. So let me see the modification of Wittig reaction. So friends, modification of Wittig reaction is known as Horner Horner-Wadsworth-Emmons reaction or Horner-Wadsworth-Emmons modification and how it's carried out. Let's see with reaction mechanism and example. So as we can see here that in case of Wittig reaction we are using triphenylphosphine and alkyl halide as a starting material, while here we are using trialkoxyphosphine oxide as a starting material. When it react with methyl acetate in presence of base, then we will get this beta phosphonate ester. As we know that next carbon to carbonyl is known as alpha and the beta position is occupied by phosphorus. So here we are writing that beta phosphonate ester. Now how this reaction is carried out. So when this beta phosphonate ester with this electron withdrawing group is react with carbonyl compound, whether aldehyde or ketone, in presence of strong base such as sodium ethoxide, sodium hydride, N-butyl lithium, and we will get alkene or olefin as a product, then such reaction is known as Horner-Wadsworth-Emmons modification reaction. Now the general reaction for this one can be defined as we have discussed here, beta phosphonate ester when react with carbonyl compound in presence of strong base to give olefins as a product. Now friends, whether E or Z, which olefins is obtained, so it is basically dependent on aldehyde or carbonyl compound which is used. How? Let's see here that if we are using sterically hindered aldehyde such as benzaldehyde, so we will get E alkene as a product, while if we are using aliphatic aldehyde like acetaldehyde, then we will get Z alkene as a product. Also in earlier part we discussed what is E and Z nomenclature and why it is required over C strands, right? So let me define this mechanism in certain detail. So when this beta phosphonate ester react with strong base such as sodium hydride in whether THF tetrahydrofuran or dioxane as a solvent, so we will get such type of charge intermediate, right? When it react with aldehyde or any carbonyl compound, so here friends we replace this carbon with R2, this group with EWG, that is electron withdrawing group, and such carbon of aldehyde as a R3. So this detailed mechanism can be explained as when this charge intermediate CH minus attack over carbonyl carbon, when this negatively charged CH minus will attack over carbonyl carbon having partial positive charge, so what will happen? This pi bonding electron will be shifted over oxygen and we will get such type of charge intermediate which is known as butane, as we discussed earlier. So as we discuss this butane, now what will happen? This oxygen having negative charge, so it will attack over positively charged phosphorus. This pi bonding electron will be shifted over oxygen and oxygen will get negative charge as we discuss here, and we will get such type of oxaphosphetane intermediate. Now as we discuss here, if we are using R3 or aldehyde is sterically hindered or benzaldehyde, then we will get E alkene as a product, and if this aldehyde having is aliphatic or like acetaldehyde, then we will get Z alkene as a product. Now the intermediate stage will remain same as we obtain in case of Wittig, that is after attack we will get charge intermediate, that is butane, then it will be converted into oxaphosphetane, and decomposition of oxaphosphate ring will gives us either Z or E alkene as a product. So by this way we can easily define Horner-Wadsworth-Emmons modification reaction for olefination. And again, the application of this reaction can be further explained with the help of example. As we are using here beta phosphonate ester, when it react with para-methoxybenzaldehyde in presence of strong base such as sodium hydride, so we will get olefin as a product. And as we have discussed earlier, that here the aldehyde which is using is sterically hindered, so we will get which one? E alkene as a product. So by this way we can easily define the first reaction of olefination, that is Wittig reaction, and its modification, that is Horner-Wadsworth-Emmons modification. After Wittig reaction and its modification, that is Horner-Wadsworth-Emmons modification, the next olefination reaction is Peterson olefination. So what is actually carried out in Peterson olefination? So as we can see on the board, that trimethylsilyl substituted organometallic compound used to convert carbonyl compound into olefin via beta silyl carbenols, then such conversion is known as Peterson olefination. How this carried out? Let's see with the help of reaction and with example and mechanism. So here this trimethylsilyl substituted derivative, when react with strong base such as N-butyl lithium, so what will happen? This base will abstract this particular proton and we will get here negative charge. Now this charge intermediate will react with carbonyl compound, that is aldehyde or ketone. Now the interesting thing is here, that is when this intermediate is react with strong base or in presence of strong base, then it will gives us Z alkene as a product, while if we carried out the reaction of same intermediate in presence of acid such as H2SO4 sulfuric acid, then we will get E alkene as a product. Now how this conversion is carried out? Let's see with the help of example with a detailed mechanism, right? So here this PHCH2CN benzyl cyanide, when it react with trimethylsilyl hydride in presence of metals such as copper or rhodium, so what will happen? It will lose H2 gas, right? 2 hydrogen will be liberated and we will get such type of intermediate. Now which is followed by reaction with strong base, that is N-butyl lithium. So what will happen, friends? This base will abstract this particular proton and we will get such type of carbanion, which is known as we have discussed here, beta silyl carbenols. Now this negatively charged ion will react with carbonyl compound, that is aldehyde or ketone, and this compound, as we know, this carbonyl carbon having partial positive charge, so it will attack by this nucleophile and this nucleophilic attack will gives us such type of charge intermediate. Now this charge intermediate will abstract proton and we will get such type of intermediate. Now as we have discussed in reaction, that if we carried out reaction of this say this intermediate 1 with strong base like sodium hydroxide NaOH, so it will abstract proton from here and we will get negative charge, and this negative charge will attack over positively charged silicon. So we will get such type of a ring intermediate, and this ring intermediate will undergo decomposition like this to give Z alkene as a product. Now in another way, what will happen when we carried out the reaction of same intermediate 1 with strong acid? So it will abstract, this lone pair of oxygen will abstract another proton and oxygen will get positive charge. Now what will happen, friends? As we know, this silyl or silicon having positive charge, and this positive charge may cause the rotation of this single double bond, as we can see here, and this group will comes out here. Now this trimethylsilyl will lose, this bonding pair will be shifted between these two carbon, and this bonding pair will satisfy the charge of oxygen, and we will get finally E alkene or E form of olefin as a product. So by this way we can easily define the next olefination reaction, that is Peterson olefination. Also, at last, don't miss to like and share the video, subscribe the channel Chemistry Online by Dr. Darshan Jani, and don't miss to hit the bell icon to get a regular notification for such important videos. Thank you very much.